the center of mass. I mean, it's one of those things that is introduced into a textbook at some point, and it's usually either too late or too early, and it's never really the right time because it's complicated. And the book I'm using for my class, 5th edition, College Physics, John Batista, and they introduce it using momentum. And I'm going to show you how to do that, but I'm going to show you the way I like to do it with torque. So a short review, and I'm going to show you this, but if in the stuff that we've done before, we had these forces mg on some object and it's moving along there, but it's just a point mass. It didn't matter where the force is applied. And we're moving into something like this, where it is a rigid object and maybe there's a force right there and maybe there's a force right there. So you can have rotational motion. You can't rotate a point. And if you have rotational motion, then the center mass is kind of important. Not 100% necessary, but kind of important. This is the equation for the center mass. I'm going to derive that. But the first thing I'm going to do is to look back over here at torque. So we define torque as kind of a rotational force. And you can calculate the torque about some point. In this case, I'm going to use point O. It doesn't matter what point you pick. I'm going to pick that point right there. Then torque would be the vector R cross F. And that's a cross product because you have a vector result. I mean, it's not a really big deal, but I do want to show that to you. Where R is the vector from the point to where the force is applied, and F is the vector force. Now, you can find the magnitude of this torque just using the magnitude of the force, the magnitude of R, and theta. So the magnitude of the torque, it's just going to be R, F, sine theta. Okay, so that's torque. Now let's imagine the following situation. Suppose that I have a one-dimensional object. This is the x-axis, and it consists of two masses, a mass right here and a mass right there. So this is m1 and this is m2. And this has a value of x1 and that has a value of a location of x2. That makes sense, right? Now suppose that I wanted to balance this object such that F net is equal to 0, which is in the x and the y direction. And let's just use the scalar version of torque. I'm going to say the torque net about point O is 0. So in order to do that, I have a gravitational force pulling down right there, m1g, and then I have one down here, m2g. I don't even know what the values of those are, and that's fine. So I'm going to have to push up somewhere with the force F. I'm going to call it Fp. And I want to find out what force I have to push up to make that be in equilibrium, to satisfy both of these. So let's start with this equation right here. We don't have to worry about the x direction. There's nothing in the x direction. So I can say F net in the y direction is going to be equal to 0. And that's going to be this force pushing up, Fp, the magnitude of it, because it's in the y direction, minus m1g minus m2g. Those are all scalar values. So from that, I can solve for Fp. Fp equals m1 plus m2 times g. I mean, we knew that, right? We knew that if the total mass of this is m1 plus m2, I'm going to have to push up with the force, the total mass times g, in order to keep it from accelerating in the vertical direction. Now, what about the torque? And so that's my point O right there. I want the net torque to be 0 also. So let's say torque net about point O. Okay, let's just start. So one of the things that we need to do is everything's at right angles, so that's going to be easy. The sine of 90 is 1. If this force would want to make this rotate clockwise, I'm going to call that a negative torque. If it would make it rotate counterclockwise, I'm going to call that positive. So, and you can use whatever you want as long as you're consistent. So the torque from this is going to be equal to negative m1g x1. Right? So it's in the counterclockwise, the clockwise direction, so it's negative. And let's do this one next. That's going to be minus m2g x2. And now, where is this force going to be? I'm going to call this, squeeze this in right here. I'm going to call this xc for the center of mass. and we'll use that in a second. And then that is going to have a positive torque plus Fp xc. So torque, 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 add those up, have to be equal to 0. I want to solve for xc. So let's just add these two to the other side. Fp xc is going to be equal to m1g x1 plus m2g x2. Now I'm going to divide both sides by Fp, and I get xc equals m1g x1 plus m2g x2. All of that divided by Fp. But now Fp I can put in that. So I get m1, I'm going to factor out the g, m1 x1 plus m2 x2 parentheses g over m1 plus m2 parentheses g. And the gravitational field g cancels. And I have my center of mass. So that is the center of mass. But what does it really mean? Okay, what does that really mean? That this is the equation, right? That's the location of the center of mass. Just to be clear, if these two have if m1 is equal to m2, then I can factor that out, and I get a 2 underneath it, and I get x1 plus x2 over 2, which is halfway in between it. So that does make sense. Okay. So imagine that I have that mass again, and I push up right here, and that's with my Fp, and it's that balance. I already know that. Well, I could say this, m1 plus m2 g. I could pretend like the gravitational force is acting at the center of mass, and that does indeed work. Okay, that works. So we don't have to deal with a distribution of masses. I can find the center of mass and then assume that there is a single force right there. So let's take an example that I'm not going to derive, but imagine I have a uniform stick, and I want to push on it right here, and I want to push on it right here. I'm just making these up, and then I can act as though the total mass, the gravitational force, acts only at that single point right there. It actually pulls on all parts of this. But mathematically, it's the same as if I put that one force right there. That one force right here is the same as the sum of the torques is equal to 0. So it gives me the same thing mathematically. And that's much easier than dealing with an infinite number of pieces of masses that I'd have to calculate the force on. So I can just have one force at the center mass. Okay, what if I don't have these in the x direction only? Well, if I have that, let's say I have a mass right there and a mass right there, and so those have an x values, that's mass 1, mass 2. Well, everything I did works, right? It doesn't matter where I put this force. It doesn't matter about their y values because the torque is only depends on the distance, the x distance from that, if the gravitational force is straight down. So I still get x center mass is equal to m1 x1 plus m2 x2 over m1 plus m2. I still get that. Now, what if I rotate the whole thing sideways? So here's my y direction. Well, in that case, my x's become my y's, so I can actually find the y center mass using the same principle. Y center mass would be m1 y1 plus m2 y2 over m1 plus m2. And suppose I could do the z direction too. Let's just write it out. Z center mass would be m1 z1 plus m2 z2 over m1 plus m2. Now I could write this as a vector. Let's call that the vector r1. Let's call that the vector r2. And then this is the location of the center mass, r center of mass. So since I'm doing these all independently and they all have the same thing on the bottom, I actually can write the r center mass as a vector equation. m1 r1 vector plus m2 r2 vector over m1 plus m2. Now, what if I have more than one center, more than one mass? Well, if I have more than one mass, I just have more than one torque, and you just keep adding to that equation. And that's where we get this. R center of mass is equal to the sum over I, mi, ri vector over the total mass, which is just the sum over I of mi. And that's how you find the center mass. Okay, now, what about the other way to do it? The other way to do it is with momentum. Suppose I have two objects right here. I'm not going to derive this one. So here I have object 1, object 2. So I have a momentum 1 and momentum 2. They have some momentums. If I want to treat this as a system consisting of 1 and 2, objects 1 and 2, then I could represent the momentum principle as F net on the system is the change in momentum of the center of mass of the system with respect to time. So I need to find that center mass in the same way. And you can add you can average the momentums. So I can do a weighted average of the momentum. The momentum of the center mass is going to be equal to P1 plus P2 divided by M1 plus M2. And then you can see I get here, this is the total, wait, no, that's it, right? But then the momentum of the center of mass I can write as M1 plus M2 times the velocity of the center of mass, and that's going to be equal to M1 V1 plus M2 V2. Now let's write the velocity as the change in position with respect to time, and I get M1 plus M2, I am deriving this, I guess, is going to be delta x center of mass with respect to time, and that's equal to M1 delta x1 with respect to time. Oh, I'm going to just do this in 1D. I should have done that as R's. Plus M2 delta x2 with respect to time. Now pick x1 equals 0. That's not x1. That's let's put reference x equals 0. So these deltas are all with respect to infinity. I mean the origin or 0. Then the times cancel, and then these deltas just become x's. And then I have the same thing. X center mass is M1 x1 plus M2 x2 over M1 plus M2. And I want to show this to you. I want to show you that if I have, this is the nice thing. Suppose I connect these by a spring so that there is some internal force from these springs, right? That should not change the center mass because this deals with external forces on the system. Well, these may move independently, but the center mass should move like a projectile motion. I'm going to show you that, and then I'll dismiss you after that. Okay. So I have a Python program that I already made, and let's look at that. So here's my Python program. Let me make this bigger. That's good. I'm going to run it, and I'm going to show you the code. You see here I have these two masses connected by a spring, and I throw the masses, but the spring's connected. So since the spring force is a force between the two masses, it shouldn't change the momentum of the center mass. Okay, so that looks nice. They're rotating around, doing all sorts of crazy stuff. It doesn't matter what they do. Now, what I want to do is to, number one, calculate the center mass, and then plot the trajectory of the center mass. And that should be a parabola. It should be just like projectile motion. So in the code, what I'm doing is making these two spheres. I'm calculating the force from the spring, and I'm calculating the gravitational force, and then choosing normal numerical calculations to update this stuff. So let's make the center mass an actual point. So I have these two masses called M1 and M2. Let's say MCOM is the center mass, and it's a sphere. How big should I make it? I should make it kind of like transparent. This sphere is radius R2 and R1. Let's say it's, I'm going to calculate the center mass first. RCOM is going to be equal to, it's the same equation I had before. It's M1 dot parentheses. M1 dot M times its position, which is M1 dot POS, plus M2 dot M, which is mass, times its position, M2 dot POS. And then I need to divide by the total mass, which is M1 dot M plus M2 dot M. That's it. Now, the the actual sphere is at that location. So position equals rcom. Radius, let's just put it as equal to r2 up to r1. And let's leave it as gray, but I will put the opacity at 0.5 so it's kind of see-through, because it's a thing. No, I'm not gonna do that. I'm gonna do this. Make trail equals true. Okay, so that just made it, but now as everything moves, I need to recalculate that center mass, and then I need to move that point. So let's just do this. Let's recalculate rcom, put it right up here in the loop, and then down here, when I move the other objects, I'm gonna move mcom.pos equals rcom, and that should do it. Let's see what happens. Something happened for sure. What the heck? rcom. M1 is the thing, right? M1, radius R2. Or I'll put R1. Let's put this as R2. Maybe R1 is not a thing. There. Okay, let's make that smaller. Let's do R2 divided by 2. I want it to look good. That's good. Nice. And you'll notice that the red mass is more massive, and so the center mass is closer to that. But what's that right there? That's a parabolic trajectory. But let's plot the trajectory anyway. So I'm going to make a graph. Do I have a graph up here? Let's make a graph really quick. G1 equals graph. Title equals center of mass. And then the X title is X in meters. The Y title is Y in meters. And then the width is 500. That's just the size of the graph. Height equals 250. And then F1 equals G curve. Color equals color.blue. And then down here, I'm going to just plot a data point. Let's plot that. I did some other stuff in here anyway. F1.plot rcom.pos.x rcom.pos.y. And now we should have a trajectory. And we don't, because I messed up. Undefined object rcom. Oh, it's a vector. It's not a position. Okay, my bad. Sorry. So I'm just going to take out the POS. It's just a vector, so I don't have a POS property of rcom. It's just a vector location. But .x and .y should give me the x and y coordinates, and there you go. Parabola winning. So those are the two ways to find the center of mass. Now, I do want to show you one more thing. I lied. I said I'd dismiss you, but the bell doesn't dismiss you. I dismiss you. There are some cases where we would like to use a center mass that we can't. You can use something. Okay. Here's my favorite example. Suppose that I have a bike, and this bike is like this. So it's coming out of the page and it's leaning, and so it's accelerating this way. In that case, we have the gravitational force at the center of mass, and then we have a frictional force right here, F friction, that's mg, and then we have a normal force right there, N. And you want to say, okay, well, what's the acceleration? If we could say m in the x direction, F net x equals m v squared over r, negative in this case. But what's r? See, because the radius of curvature is at different points. And you say, well, I'll just use the center mass. But that's actually not right, because you would have to find the center of acceleration, and it's not the same thing as center mass. The same thing happens over here. Suppose I have a giant person standing near the earth. I mean, super giant. So that there's a gravitational force on the feet, there's a gravitational force on the head, but it's not constant. In that case, the center of mass or the center of volume is not the center of gravity because the gravitational force is not constant. So there are some cases where you can't use just the normal center of mass to point the gravitational force, or if you want to use the acceleration of the center of a turning thing like that. It just doesn't always work. I'm just telling you right there, that's true. Just be careful in some situations. If you use the center of mass as that we used before for this, it'd probably work fairly well, but it's not perfect. And you're probably not going to deal with giant people like that anyway. So there you go. The end. Center of mass. The torque weighs the best.